So hello students, how are you? So today we are launching another course that is CMOS in VLSI. So in this course we will going to discuss like what are the concepts that are important for the test purpose and what are the important topics that they ask in the interview. So this is a particular course we have launched for the already we were covering this topic in the old courses, but separately we have also launched it right now. So yeah, so let us see what are the, and it is for the VLSI only, like what are the important topics they ask in the VLSI particularly. Yeah, so these are the syllabus. It is around 20 to 25 hours of the course with the theoretical concepts plus some numericals. Numericals will be also there, and some interviews question will be there, right? Interviews, preparation questions of CMOS related to the CMOS. Yeah. So what are the topics we will going to cover in this? Introduction of the MOSFET, working principle, regions of operation, formation of oxide capacitor, CV curve, then CMOS fabrication, then CMOS NAND and NOR gate implementation, pass transistor, tri-state, multiplexer, what are the different type of powers in CMOS, then interconnect concepts. Then we will going to discuss the delay modules like RC delay modules and envelopes module. Then we will going to discuss the logical effect of path. Then further we will going to discuss the combinational circuit pitfalls. Yeah. So these are the major topics we will going to cover. We will going to add some more topics as per the requirement of the course and depending on the faculties, right? And if you want some more topic, we will going to discuss these things. These are the major topics that we will going to cover in this course. Yeah. So for the further information, we are giving the demo class of the faculty also. You can watch the demo class, and in the demo class ma'am will be telling you how are the concepts, what are the concepts and how we are covering all these things. So I will attach the demo class in this class only. Yeah. So now for the further information you can contact us to the website. You can come to the VLSI For All website. You can it's vlsiforall.com. You can come to the free counseling. So this is the new number we are using right now. Old number is not working for 1 month due to some technical issues. So most probably by the 20th of February it will be working. But since old number is not working, you can contact this number. But this number is for the WhatsApp mainly. For the calling purpose, you can use the old number only. That is 9643 070 368. This is for calling number and this is for WhatsApp number. Another thing is download the VLSI For All app. Where it is available? If you go to the website, sorry. In the bottom of websites you will get the link to download all everything, right? This is the thing. Play Store, App Store, Windows version, all the versions are there right now. Furthermore, yeah, Windows it is also available right now. Yeah. Furthermore, there is one more website we are using for the test series purpose. This .in website, vlsiforall.in. If you download the VLSI For All app, there are some free courses. There are some free courses like around 50 free courses are there right now. We will going to upload more free courses in the app. So if you like the free courses, then you can go for the paid courses for the complete knowledge and with a mentorship and everything, right? So yeah, free courses are available with a certificate. Whenever you complete your free course, you can write the mail to this ID so that we will generate your certificate, right? So you can write we will going to cross check in the back end of the application and we will going to generate your certificate immediately. Fine. So this is the process. Yeah. So I will going to attach the video of them. Oh, okay, fine. Thank you so much. If you have any further query, you can contact on the WhatsApp number. This is the WhatsApp number we are using. For that, within 24 hours, we will going to call you and we will going to discuss the queries. Thank you so much.
Good morning, everyone. So today we are going to start a new lecture series. It will be a short lecture series, and we'll focus on the digital CMOS world and what are some of the important concepts of digital CMOS which are useful for getting a job in VLSI industry or maybe important for cracking a VLSI interview. I mean, these are some of the basics one should know, and definitely there have been questions in the hardware based companies which where the interviewers have focused on questions related to this particular digital CMOS background uh, where you have to know the basics. And I mean, they definitely go with one or two questions from this topic when they are interviewing you for any particular job, especially for all digital roles. So let's begin. uh, 1 second. Yeah. So this is the syllabus. I mean, I have written it on a very super. There is something on chat. My voice is not clear.
It is fine.
I mean, is there any? Okay.
Fine. Just continue.
Okay. So this is the syllabus and written it at a very higher level. There are definitely subtopics to each of them, but at least getting an overview like what will be covered. So first one is once again, yeah. First one is the introduction to MOSFET, which involves basic operation and the basic working and regions of operation. So this will be mostly kind of revision for you all, where you will understand what you have studied in your BTech days. Then there will be the next topic, which will be about the formation of oxide capacitance, how the capacitance is formed between the gate and the substrate. And finally, we will also study the CV graph. After that, we will focus on the third topic, which is CMOS fabrication. And we'll go through the entire steps how CMOS gets fabricated. That is from the layer 1 to all the final layers. I mean, what is the exact realization of a CMOS? And then we'll have NAND and NOR gate functioning using the CMOS circuits. So this here we'll also study how it behaves as a how it behaves as a resistance and how it conducts current and the logic functionality of NAND and NOR gates. Then we'll use the CMOS for pass transistor, tri-state buffers, as well as multiplexers. So we'll see how CMOS is useful in other important digital functioning, which is switch, then tri-stated buffer, as well as multiplexer, which is also one kind of a switch. So this is this is one other important topic. Then we will study about all the different powers and all different type of leakages that happens in CMOS, a very, very, very important topic like around dynamic and static power dissipation, which takes place in CMOS. So here we'll see some of the pitfalls of CMOS, as well as what are you will also study it about sleep cycles, or you can study about gated MOS. So all these there will be different ways how we can try and save power in CMOS, and these are being realized in the industry as well. Then there is another topic called interconnects, which will come where you will see how charge gets distributed and it causes leakages because of connections between the CMOS circuits. Then we will have a realization of CMOS into RC models. And because of this RC, I hope everybody has read network theory in their BTech, that RC circuits leads to delay, tau, right? So delay model will be there, which will basically be the realization of a CMOS into just RNC and multiple CMOS will always called consecutive delay, which is also known as Elmore's delay. We'll study this concept. I think this will take around 2 to 3 lectures. And then followed, I mean, this the eighth and ninth is like connected logical effort of paths. These two are, I mean, these are similar topics like delay part 1 and part 2 I have distributed. And finally, the last thing we'll see are some of the combinational circuits which are made using CMOS, and what are the challenges that we are facing, that we have faced in these circuits, which will help you understand like what are the what are the basic challenges that CMOS faces and why the new circuits started coming into picture. So before proceeding on, okay, how many people are there? I understand there might be 8 people apart from me and Rajat who have joined. All of you are either on the verge of completing your BTech or have done your BTech. So just tell me where all, I mean, what were the different flavors of CMOS that you had studied or that you have studied or that you are going to study in CMOS? I mean, we have seen CMOS in our entire 4 years in different forms. So just let's recall what were the different flavors of CMOS. I mean, just one round of open session before we proceed on with anything else. Let's see. Which subjects did you study CMOS? Sorry?
Yeah, actually we have CMOS, NMOS, PMOS. I mean, the combination of those. I have read it in the VLSI design and the op-amp.
Yeah, that's right. CMOS is a combination of NMOS and PMOS. Okay, so one is one I think you mentioned is analog CMOS. So there was a subject called analog CMOS where we studied the small signal analysis of CMOS, and there we were basically studying about the AC characteristics of CMOS, right? I'm talking about the same subject where you studied op-amp. So your CMOS was also realized into input resistance, output resistance, input voltage source. There were circuits you made like that. Emitter, sorry, not emitter. I mean, this will be your gate. Anybody remembers such kinds of circuits you used to make?
Yeah.
So this was one flavor where we studied the small signal analysis or the AC characteristics of CMOS, right? When I mean to say AC characteristics, what do I mean? I mean to say that my input, the input voltage source, which, okay, let me, 1 second. Let me say, let me draw it here. For example, this is my CMOS, okay? This is my gate, source and drain. Now, this is my NMOS, sorry. Now, let's say when I'm saying AC characteristics, what do I mean? I'm trying to supply a AC voltage source to my gate. Only then I will do the AC characteristics or the analog analysis of my CMOS. I mean NMOS or PMOS, whatever. This was, I'm just showing it on an NMOS to make you understand what all we have studied in CMOS and what will be the agenda of this course. First, we need to understand what are we studying. I mean, it's not like we have been given a course and we have to study. We should know why, what are we studying and what all we have studied till now. Okay, so what was the next flavor of CMOS or next subject of CMOS that you saw? Anybody?
हम खाएंगे नहीं
Sorry?
हाँ ठीक है डालो तुम आज मैं खाऊं नहीं सर
Yeah, can you please mute yaar if you're not speaking content relevant. Okay, so another flavor that I can say is digital CMOS, which is definitely what we'll study in this course also. in digital CMOS, we study, what do we study? I mean, what all we have studied till now? 1 second.
Or gate and gate
Yeah,
and
yes.
gate.
So in digital CMOS, you people would have studied like, okay, PMOS is on. Let's say PMOS is on and NMOS is off, right? So conduction is happening. Which way? This way,
Hotspot on.
right? And let's say if NMOS is on and PMOS is off, the capacitance is discharging through the NMOS, right? So you would have studied switch, you would have studied NAND gates using or NOR gates using CMOS, or you would have studied, although this topic is very, very less covered in our BTech syllabus, but I'm just trying to say that this is the main focus of our of this course, and we'll study what is all there in digital CMOS and what all things can happen when you just, so okay, the input voltage applied to my gate will be digital this time, right? It will be digital, so I'm giving VDD. In analog, I was giving an AC voltage. So this makes us understand, okay, we are working in the digital world for my CMOS. My agenda is will be digital. So much what I'm able to recall, I mean, in my curriculum, this part was done, but not, I mean, it was not of much relevant, and nobody stopped here. This is from where the digital VLSI journey begins, okay? From this digital CMOS. Okay, what is the other flavor of CMOS that you have studied? Anybody else that you point, okay, you got to study CMOS here also? Two other basic ones. Okay. Anybody else who can think, okay, I studied CMOS here also?
Ma'am, from fabrication perspective.
Yes, fabrication perspective, that's correct, but it's like I mean, everything is analog also fabrication perspective, digital also fabrication perspective. CMOS fabrication is almost, I mean, let's say that once it is done, but how do you work? I mean, in what all regions or what all ways you are working, we are trying to identify that. So one was power, power MOSFETs also you would have studied, right? Power MOSFETs, so they deal with, 1 second. Yeah, power MOSFETs deal with extremely high voltages. Extremely high voltages. So there were a couple of different types of CMOS circuits that you would have studied here. You can check maybe your EDC or I don't know what is the curriculum name that you call. EDC is what I would like to say. Okay, and what else? Okay, there is one more new top called nanotech. I know in BTech, 99% of the colleges don't teach nanotech. If it's an optional subject, then it is okay. But I don't think most of us opt or even go for this. But nanotech means, I mean, from where this nanotech terminology is coming into picture is, you know, MOSFET, right? Like for example, if I'm just drawing NNP region. Yeah, please mute, yeah, please mute. Okay. Okay, let's say this is a basic basic MOSFET that I've drawn, okay? Basic CMOS I've drawn. The channel length, and let's say my channel length is reducing and reducing and reducing. So you would have heard your seniors or super seniors saying, Array, today I'm doing a 7 nanometer technology, or I'm working on a 14 nanometer technology. Friends from Intel would have been saying, I'm working on a 4 nanometer technology. Someone would have been working on 180 nanometer. I mean, the colleges the colleges would be working on 180 nanometer technologies. Is there anybody who's familiar with these terms? Have you heard this, or is it like you're completely blank on? Please at least let me know so that I can understand how the audience is. Has anybody
Yes.
heard of okay, someone is there that he's familiar, but you would heard people saying ki I'm working on a SOC of 7 nanometer or a 14 nanometer or a this 28 nanometer or and so on, right? So this is basically your length of the length of your channel. The channel length is reducing day by day by day by day. 4 nanometer it has come, someday it will be less. Yes, sorry. Did anybody say something? Oh, man. Okay, so nano comes from this effect only. When you're reducing channel length, what are all the different phenomenons that MOSFET is going to suffer? MOS is going to have supreme amount of leakages as you reduce the channel length. There will be different short channel effects. If somebody has studied this term, short channel effects, for example, drain induced barrier leakages, or there can be, there are around 5 or 6 effects called short channel effects which start occurring once you reduce the size of these devices. And because of that, we are giving enhancements to CMOS. Structural enhancements to CMOS, from where the term comes, nanotechnology. Like when you're working on nano scales, what enhancements are you doing to your CMOS fabrication to make them avoid all the different challenges that can happen? Okay, FinFETs, and there are numerous amounts of research which is going on as of today, because we are reducing our channel size and we are trying to fit numerous logic into the smallest amount of area. So since we're trying to reduce area, what is impacting power is static power dissipation is increasing. Okay, so this is one nanotech side of the CMOS. This is one another flavor. So we studied analog, we studied digital. We have also gone through power MOSFETs, although very briefly, but then there was one side. Then we have also studied nanotechnology. Then you have not studied nanotechnology, but one can go for a specialization in your MTech for nanotechnology if you want to move to VLSI. Anything else that I am missing or you know? Okay, cool enough. So these were like some of the places where we had studied MOSFET in our BTech, or maybe you might be planning to go for MTech, or let's say if not MTech, for an industry of VLSI, then these, I can say, these two are something which you can think about reading or getting a specialization into. So, for us, we are going to focus only on this part of CMOS. So if someone is thinking, oh, I'm not able to see the AC characteristic analysis in the syllabus, or let's say I'm not able to see some other analog part of the CMOS, there are no CMOS analog questions. Because it's not the agenda for our today's class. Not for today, for the entire syllabus. Okay. Okay. Any questions before we proceed? Today I'm generally keeping it as an overview session, or maybe you can call it a revision session, so that you can get familiar from maybe next class.
We can continue. No questions.
Sorry?
No questions. You can continue.
Okay. There is something on chat.
Hello, ma'am.
Yes.
Yeah. In MTech, is there any specializations like we have to choose a PD, DV, or DFT?
No. Such kind of specialization is not there. There is just that you can do a VLSI or a nanotech based degree.
Okay, okay.
Okay, so starting on with the first module, which is like introduction to the MOS family, the basic operation and the different regions of operation. So first of all, let's see what all you people know from the, I mean, when you see this topic, what is that you all have studied till now here? Because, I mean, I also will not be sharing that much of theoretical resources as you already have so many books, internet, I mean, so many blogs are there, so many good websites are there. So just sharing the theory part is like iterating and doing that same thing again. It's better we keep focus on the conceptual and the understanding part of it. So I mean, first let's see what all we people have known till now on this end. Just focusing on this end. I mean, anything, anything that you know about MOSFET.
Basic working would be, it is a current flow from source to drain. And then region of operation, I have here heard about depletion mode, enhancement mode, and inversion mode.
Right. Sorry, 1 second. That's correct. So you have studied about different regions of operation, and then you have also studied different types of MOSFETs, the enhancement MOS or the depletion MOS. And then you have also studied about the basic, there would be different like characteristics of various graphs that you would have drawn for MOSFETs also. So that is right, like at least you are familiar that, I mean, the basic terms around CMOS. And I think someone has asked a question, will dynamic CMOS and low power concepts be covered? We'll cover, we'll not be covering the dynamic CMOS, but yeah, low power we can cover in the power section of our MOSFET. Okay. One second. Okay, now let's come to some of the. I've written basically what were some of the things that we had studied and what all we know about the MOS family. Okay, so what was there earlier? Earlier there was just PMOS and NMOS usage. So if you go back to Intel 4004 or the earlier processors that were there, they were just using either PMOS or they were just using the NMOS. So history recalls only PMOS and NMOS, but not a CMOS family. But today, as of today, we are using CMOS based circuits. I'm not saying that we're using a CMOS. I'm saying a CMOS based circuit because the heart of it is CMOS. But yes, as I've told that since we are driven into this nano world and we're working, I mean, the technology is involved and Moore's law is also almost failing every day. So the heart of it is still CMOS, but yes, there are enhancements to it. So CMOS is as of today still there in most of the companies, and we are working in this CMOS family. Coming to the next characteristic, which is packaging density. So obviously we needed a device which could help us in large scale integration. What do you mean by this large scale integration? Even your VLSI has this LSI term. What does that mean?
Incorporating many IC chips, I mean, many circuits in an IC chip.
Yeah. So incorporating a CMOS circuit or CMOS based logic as much possible into a single chip, right? That is called as large scale integration. And your VLSI is what? Very large scale integration. So for that, you need such circuits to come and make all the logic blocks. So that is why CMOS was found to have a very, very density. So any guesses on how many CMOS, I mean, how many transistors can be there on a single chip as of today? I mean, just a random number you can guess off.
Billions of transistors on chip.
Sorry?
Billions of transistors.
Correct. So the number has obviously is, I mean, it's in billions, right? So, I mean, billions of transistors are there as of today on a single chip. And that chip can be based on your any of the application. If it's a memory based company, a memory controller would have that many chips. If it's a modem chip, it would have that many transistors. If it's this graphic based, I mean, let's say NVIDIA chips, graphic cards they have, right? They have graphic controllers and graphic controller on their chips. The main purposes of that, they would also have that many transistors. So packaging density is one of the biggest point for this MOS family. Then coming to operating speed or propagation delay. So we all know that MOS logic family has a very high output impedance. And that is why we have a very large delay of about 50 nanoseconds. So it does not mean that you can, I mean, quickly, you can, I mean, this has it's both pros and cons. You can understand like not as just as a con or not just as a pros. I mean, if the speed would have been very less, it would just be like a, it would just be like a bulb. Let's say if it was 1 nanoseconds on and off. But no, CMOS also has regions where both PMOS and NMOS is on, right? Why? Because your capacitance at that time is charging. The output capacitance is charging. So that is why it has called high output impedance, which leads it to, your CMOS can function in so many ways. We saw it earlier, right? The flavors of CMOS. So these are the different ways where your CMOS can function. And in digital world, it will always have a high output impedance. Then coming to power dissipation. What does power dissipation mean? The amount of power which is used by the logic circuits. Right? Now, power dissipation will be significantly high for MOSFET. Why is it high? This is a gate. Gate is made of metal. One second. Gate is made of metal. Then you have oxide. Oxide, you can consider it as an insulator. Right? It will not conduct until you change its properties. And then you have a silicon here. Correct? So, this is your source and let's say this is your drain. Now, let's say if you're trying to, now from where is the input source? Input source comes from gate, the VDD. Right? But for any conduction to happen, you have an insulator sitting in between the oxide. So my input resistance is high, right? And what is power dissipation? What is the formula of power? I square R. Right? So since conduction will be significantly low, we can say the resistance will be very, very high. Your power dissipation will also be high because of the input resistance, which is high. Okay, then coming to noise margin. So ability of a device to withstand noise. So MOS devices can take less than 1 volt. The noise they can withstand is less than 1 volt. They will go to breakdown regions once you start increasing beyond their capabilities. Like if there is a V minimum to V maximum and you start supplying beyond that, they will not be able to take it, they will not be able to hold it for long. They will burn out. So the capability of the device to withstand noise is known as noise margin, which is typically low. Coming to voltage levels. So 3 to 15 volts, 9 to 15 volts, you would have seen. There would be different types of MOSFETs working on a higher voltage range also, like I told about power MOSFETs. I'm just talking about the simpler MOSFETs that you see as of today. So these are the general ranges of voltage. You would also see MOSFETs working on 1.8 volts, right? Not even starting from 3. These are some bookish, you can say, what was there before, but today, like when I see in industry, it's 1.8 volts or 1.2 volts is the digital world. Okay, so this is the application of voltage levels which you see in the MOSFET. I think I've repeated this power dissipation point, but yes, one more point. Let's say about DC power dissipation and active power dissipation. Now, when will DC power dissipation happen? Like I told, either my PMOS is on or my NMOS is on. One of them is on. So at that time, my MOSFET is behaving like a switch, right? You know about this, right? When does MOSFET behave like a switch? Either your PMOS is on or your NMOS is on. We will discuss all the mathematics behind this. Like you don't have to ratify why PMOS is called a switch because PMOS is on and NMOS is on. I'll explain all the things, but I mean, just we are trying to recall what we have studied, but we'll discuss the maths also behind it. Okay, so like let's say I'm drawing a MOSFET, okay, and this is my capacitance at the output, this is my VDD, and this is my gate. Okay, gate, and I'm supplying V input. Now V input can be 0. V input can be either 0 or it can be either VDD. V input can, 1 second. Yeah, V input can be either 0 or it can be VDD. When it is 0, what will be on? When V input is 0?
PMOS.
PMOS will be on. And when V input is VDD, NMOS will be on. So when PMOS is on, the capacitance will start charging from VDD like that. And when your NMOS is on and PMOS is off, your capacitance will start discharging towards the ground. Right? So here it is behaving like a switch. Like when V input is 0, V output is, when V input is 0, V output is charging from VDD. So V output is close to VDD. And when V input is VDD, your capacitance is discharging. So it is losing its charge, and that is why it starts coming down to 0. So it behaves as an inverter, right? It behaves as an inverter. So this is called as DC power dissipation. And momentarily what happens when one is trying to become off? Let's say PMOS was on and NMOS was off. But now I'm trying to switch. I'm trying to make my NMOS on. So momentarily the time will come where both will be on together. Very delta amount of time you can take. And that time there will be, like, let's say this is also on and this is also on. So at that time, what will happen? Current will start flowing from VDD to ground here. Right? ID current that you study. That will start flowing from VDD to ground across PMOS and then NMOS. So this is known as active or dynamic power dissipation. Okay. So this is another kind of power dissipation that will happen. Any questions till now? Before we move to the structural details of MOSFET. And again, requesting, please don't expect much of theory to be given to you. We'll work, I mean, theory is there, theory is available on internet. So slides will have less data, but more to listen. Any questions?
No, ma'am.
Okay. Okay, let's come to the basic structural details. Like as you can see, there is again no theory in this slide, but we will discuss how a MOSFET is made. Not the technical details of the fabrication. I mean, that will be a separate lecture, but at least like the meaning of this MOS, metal, oxide, and semiconductor. So, I mean, the example that I've taken is of the N-channel MOSFET. Why it is called N-channel, you will be understanding when we will discuss it. But I'm taking an N-channel MOSFET. So from this picture, what all can you make out? What is this? Blue, the light blue region?
Substrate.
Piece of
Yeah. So is it highly doped or is it lightly doped? It is always lightly doped. It is always lightly doped. Why is it lightly doped? This is your homework. Okay. I want to know why is it lightly doped? Why is it not heavily doped? Because always you see the source and drain are written as N+. N+ means heavily doped. Got it? These are always heavily doped. I know the answer, but I don't want to give the answer because I want you to do that homework. Just go and fetch in your books why the substrate is lightly doped.
Ma'am, if it is heavily doped, then there is a chance of formation of NPN transistors.
Good. Good. One way of understanding is that there is a chance of forming a transistor here itself, which is he has told an NPN transistor. But you can also understand it in another way, which you can again think of. I mean, I'll ask again to just go back and read why. I mean, what will stop it from? Okay, one is that it will become an NPN transistor, but what will? I mean, what? How will it going? How will it stop the functioning of MOSFET? Just try to think in that way. So as we can see, substrate is something which will support the device and everything will be fabricated on it. So, I mean, mostly you can also think it like the first, like we can say that even in the fabrication, the first step would be to create this big substrate, right? The lightly doped P substrate. So there can be ways called diffusion or there can be different ways where you can create this substrate. Then you have to create your two heavily doped N regions that are formed into this substrate through again a process called diffusion, right? So you would be etching out the material from the P substrate and then you will be depositing the N material. So somewhere you can understand the fabrication here itself. Although we'll revisit it, but you will create heavily doped regions called N. Then these N regions will start acting to you like source and drain. So you will start giving the electrical contacts of source and drain to this N region. Now what is the next step? Next step is the formation of this dielectric or the oxide, and its nature is the exact nature, if you keep it untouched, how will it behave? It will behave like an insulator. So it will prevent any kind of conduction unless you change its programming. I'm saying it programming, the voltage programming. So there will be a thin, not a thick, a thin. Again, you have to study why is it thin and not thick. Anybody? Why is it thin? This is also homework. Or you can keep thinking and yeah, someone is saying.
Capacitance effect.
Sorry?
To have that capacitance effect, if its capacitive effect will be more if the thickness is thin and if the thickness is small.
Chalo, we'll come to this. Okay. Okay, so this is thin. So a thin SiO2 layer is grown over the structure through the oxidation process, where this oxide layer will act as an insulator. So the process here will be oxidation process because we are putting SiO2. Here we were doing deposition. Okay. Now, a portion of the oxide layer is removed to expose the source and drain regions. So generally what happens initially, the oxide layer is grown through the entire top. Okay, these electrical connects of source and drain happen at the very, very end. But before this, the oxide layer is grown throughout this region. And then you chip off the oxide, or I mean, you etch the oxide from places where you have the source and drain. But I mean, can anybody think you would have never seen a oxide chipped off? I mean, it's not completely there. There is always some part of it intersecting with the source and drain. You would have never seen that. Homework again. Why? And these will be covered. Eventually, you will understand these things also. But I mean, just think of it, right? If you're etching it, etch it fully. Now, why you're keeping even the small delta regions overlapped? Correct? Is the question correct? I mean, is the question understandable?
Yes, ma'am.
One should know the structural details. Let's say someone puts you this kind of an oxide. You can simply point it out. Oh, no, this is correct. This is not correct. You have to give some margin to it. Okay, moving on. So once you have removed that portion of oxide which was exposing the source and drain, then you can make your electrical contacts to source and drain, which you can already see in the picture, but they don't happen immediately. They only happen after the oxidation process is done and it is etched out. Then finally comes the metal deposition, right? So metal layer is deposited over the oxide layer, and that covers the region between the drain and the source, and this metal layer is also known as the gate. So sometimes electrical contacts are not made again, and the gate also deposits here and here everywhere. Again, it is etched out, and gate comes directly over the oxidation top. And again, you can make electrical contacts to source, drain, and gate. Understood? This metal layer is acting as gate. So this device will have a metal layer on the top, the oxide layer in the middle, and the semiconductor structure at the bottom. Hence, it is called as the MOSFET. So enhancement type of MOSFETs. Somebody mentioned the two terms called enhancement and depletion type. What is this? The photo, what is the photo showing? Is it an enhancement type or is it a depletion type?
Enhancement type.
Sure. Yes, so that is correct. This is an
Yes, ma'am.
enhancement type. Yeah. So enhancement type of MOSFETs do not have any physically fabricated channels. What do I mean by channels? That they are completely in non-conducting mode. I mean, there can be no conduction happening just merely by giving the gate voltage. Depletion MOSFETs, however, come with an idea that, a channel is established where I have electron, 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 electron. Just supply the voltage and the conduction will start happening. What did I do? Current, yeah, ID. Current will start flowing from source to drain. So they come with the formation of channel. Although formation of channel is not a physical, what do I say? It's not like you have a hard line of channel being formed. It is not a process like that. It is also an electrical process, but they will not have a channel. Okay, so this was an enhancement type MOSFET. Any questions? We'll come to voltages now. So there are two important voltages of this N-channel MOSFETs, VGS and VDS. And one request, since we are not going to do everything for PMOS, the P-channel MOSFET, so you can consider it as either VSG, VSD, or you can see it as a VGS mod or a VDS mod for PMOS or for PMOS again. Cool? Not PMOS, sorry, what am I doing? P-channel CMOS. P-channel CMOS and N-channel MOS and P-channel MOS. Okay? Clear? Is there any confusion? Please tell me now. Otherwise, everything will just go above the head after this. So, working in regions we'll do in the next class. But I mean, let's take the different voltages, which is VGS and VDS. So VGS is obviously like VGVS. So VG minus VS becomes your VGS, and VD minus VS becomes your VDS. I mean, the most basic thing you should know. So what does VGS means? I mean, what is the meaning of it? VGS is applied to form the channel, and for our NMOS, it is obviously positive. So VGS should be positive and it is applied to form the channel. Now I am introducing plus here, right? Why? Because my supply VG is positive. So what will be the polarity inside the gate? Positive, because of VG being positive. Now there is a polarization effect that will happen in my SiO2. You can go and study in your physics, or if you remember, they start polarizing. That means it starts separating into positive and negative. How? If there is positive towards this interface between the gate and dielectric, negative polarization will come here, and negative charge will come here. Negative charge will come here and positive charge will come here. This is known as polarization effect. Okay. Now, what will happen? Between the dielectric and the substrate boundary, charges will start getting attracted to this plus at the interface. So from here, electrons will start flowing upwards from the P substrate. And in the P substrate, my electrons are minority carriers. If anybody remembers, majority carrier is equals to Ni square, intrinsic concentration, upon minority carrier. So if okay, leave it. So my because of this positive charge here, my electrons will start coming towards this interface boundary because opposites attract. Since electrons start coming close to this boundary, it will form a dense area populated with my electrons that will form the channel. Everybody able to understand this? How channel formation takes place? You keep on reading books, but I mean, this is the way you should understand how MOSFET starts behaving in the conduction region. So VGS1 starts becoming positive, gate polarity all will, since it's a metal, it will be positive, positive, positive. dielectric will have its polarization effect with the kernels being formed, and you can take the opposite polarity like plus here, so minus here, plus here, and all these positive ions in the dielectric will start attracting the electrons, which are the minority carriers, from the p substrate, and this will help in the formation of a negatively charged region full of electrons, which is going to conduct, but it will conduct only when your VDS is applied. Once VDS is applied, that means you're trying to pull the electrons towards this positive region. Why? VD is positive. Electrons will now start moving towards the positive side. So electrons from source to drain move here. Cool? Which is the direction of my ID current. Can everybody visualize it now? What is the functioning of VGS? What is the functioning of VDS? And from here, we'll continue the phenomenon of where the threshold voltage concept comes. I mean, I'm stopping the logic part here, and I'm going to start the working the regions of operation in the next class. But anybody, any doubt? Or is it like it was too fast and nobody was able to follow up? What happened? Hello?
No, ma'am, it's understood.
Any doubts till here?
No, ma'am.
Anyone have any doubt
No, ma'am, no.
regarding syllabus or anything or regarding registration? Anyone is new who is not enrolled? Yes, Paras is not enrolled, and Purna side user is also not enrolled, I guess. Yeah. If you have any query, you can coordinate on WhatsApp. Thank you. Thank you, ma'am.
Yeah, thank you, everyone.
Thank you, ma'am. Thank you, ma'am.